Hi guys, how are you doing? I hope you're doing great. This is Teacher Smile, and today we are looking at differentiation from first principles, but that's not where our focus is. Our focus is on where exactly is this formula coming from? Where is this formula coming from? Of course, we need to understand this first. Whenever we are dealing with differentiation, we are going to see ourselves meeting these things again and again. F prime of x, y prime, dy over dx. They all mean derivative. And derivative is the answer that you get from differentiation. So in other words, differentiation is a process of getting that answer. When you get that answer, it's now called the derivative. It's very important to understand that derivative is actually gradient. You are actually calculating gradient. So look, when we have a Cartesian plane, like this, and on that Cartesian plane, we have a straight line. Let's just make something straight here. We have a straight line here. And I have a coordinate here. This coordinate is 2, 4, let's say, and this one is, let's say this one was A, this one is B. Let's say this one is 3, 5. Yes. So this is a straight line. And on a straight line, we can calculate the gradient of a straight line this way, because there are two coordinates given. Which are those two coordinates? 2, 4, and 3, 5. The equation of a gradient is y2 minus y1 over x2 minus x1. Then we need to understand all the coordinates on the Cartesian plane are written in the form of xy. So this is xy, this is xy. But now we have two of them, so I can choose these ones to be x1, y1. This one is x2, y2. Now I substitute, instead of y2, I'm going to write what? 5, subtract 4, all over 3, subtract x1, which is 2. So the answer is going to be 5 minus 4, that's going to be 1 over 3 minus 2, that's 1. So the gradient for this one is 1. Well, easy peasy. We now see that the gradient here can be calculated this way and we don't have any problem. Okay, let's try to understand something else. When we are on a Cartesian plane, let's say this equation that we were given is actually f of x is equal to x plus 2. Then the point A was at 2, x on the side of the x-axis. This one is y-axis. This one was y-axis, and this one was x-axis. So this was 2. How would we get this part? We would get that part by f of 2. Meaning I'm going to substitute 2 here, and I get 2 plus 2 to get what? 4. Right? If there's a 2 here, I substitute this 2 into the function to get the answer for y. That's the same here. If I have another point here, let's say that point, I go to the right by, let's say I go to the right by 1. This answer will be 2 plus 1, right? Which is equal to 3. And here, I will plug it in the function again. That's still 2 plus 1, right? Yes, very important for us to understand what's happening here. We just have this 2, and we are plugging that 2 in the function to get the answer here. So when we plug in 2 here, we just mean it's f of 2 and we get 2 plus 2 and we got the answer to be 4. And this side, that's where you see that 4. When we plug in 2 plus 1, that's 3, right? So we need f of 3, which is equal to 3 plus 2. Where there is x, I'm now plugging in 3, and the answer is equal to 5. Like what you would see here. So here it's 5, right? So we have all these, this side. They can be generalized. We can generalize everything here. Let's say I had that. So it means this one, I can put it as x. I can have this one as my x. And if the distance here is known as h, like 1, like we're saying, what distance am I going to the right with? This part is going to be known as x plus h. But as you know, this side is always plugging this into the function. It will be f of x. And this one coming here, it will be f of x plus h. Assuming that this is A, this is B, if I want to write this as coordinates, just like how we were writing this as coordinates, that this is 2, 4, 2, 4, this one is 3, 5, this one is 3, 5, B. We can still write our coordinates that we're starting with our A. This will be x and f of x. And our B will be x plus h, x plus h and f of x plus h. We will be making this one, x plus h and f of x plus h. This and this, they make this coordinate of A. Now with this, we already know how to find gradient. Gradient, we have to make sure that these ones are labeled first. This is my x1, y1. This one is x2, y2. So if I want gradient, gradient will be equal to y2 minus y1 all over x2 minus x1. So what's my y2 here? My y2 is f of x plus h minus this one, y1, which is f of x, all over x2 is x plus h minus x1 is x. And we can easily see that x minus x will go away. This x and this x will go away. So we will be left with what? All in all, we will be left with this answer for our gradient, which is f of x plus h minus f of x all over h. But listen, guys, we understand that when we have a straight line, the gradient everywhere is equal. It means that the gradient here, and the gradient here, and the gradient here, and the gradient here, here, and there is still the same because it's a straight line. Remember, gradient means slope. When you're talking about gradient, we are talking about slope. So you can see that the slope here is still the same. It's not changing. But what if the slope is actually changing? Let's say I have something like this, to be precise. And I have my A that I have already said is my x, and I have my B, which I have also said that is my x plus h. And this one, we already said that is my f of x. And this one is also my f of x plus h. Just continuing from here. But you see that if I am to calculate the gradient of a line that passes through these points, these 2 points like this, that is what we called M that time when we were calculating. We called that M. We called it that M. We said M is equal to f of x plus h minus f of x all over h. That's what was left. But I want gradient here. I want the gradient here. I want to know the gradient here. Gradient at a point in curves. Remember, the gradient here is different from gradient here. It's different from gradient here. It's different from gradient here. So this line that is known as the secant line cannot represent the gradient at a point. The line that can only represent the gradient at a point, at this point, is a tangent. A tangent is a line that does not cross twice. It just touches this part and it will not get inside like this. So if we are thinking, ladies and gentlemen, what if I start reducing this distance? This distance, that's what you called h. If I start reducing this distance, let's say I reduce it, it comes here, the x plus h comes here while the h has been reduced like this. I'm going to have a secant line that's going to pass through these 2 points. And then I think again of reducing this. Okay, I need to bring it right here. And I'm going to have another secant line that's going to pass through those points. Okay, fine. Let's reduce it further. And we need it to come right here. Okay, we'll have a secant line going this way. And if this point, this h keep on becoming smaller and smaller and smaller, and we no longer have any h at all, we no longer have any distance between these 2 points, which means we drag this point all the way here. We are going to have what? We are going to have our secant line looking exactly like a tangent line. So this line is no longer a secant. This line is a tangent. And a tangent is the line that represents the derivative, that represents the gradient. So the way to write all this is now by saying the gradient of the tangent line will be equal to, now I say, we need to reduce h to go to 0. If we take this distance from here to there, if we keep on reducing it like the way we did here, and we reduced it, and we reduced it, until the distance here is none, which means this point is right here, then the secant line is going to be the tangent line. So as this becomes equal to 0, then the gradient of the secant line will definitely be equal to the gradient of the tangent line. So this is where the formula is coming from. We need to understand that when the secant line, we keep on dragging it, we keep on dragging this point, we bring it here, this secant line will look exactly like this. If we drag it back and put it here, this secant line will look like this. And if we keep on dragging this point, bringing it right here, the secant line will be the tangent line. As this distance we called h is going to keep on decreasing to be equal to 0, then the gradient of the secant, this one, is then going to be the gradient of the tangent. This is what helps us to understand where this formula came from. All right, thank you so much. Don't forget to hit the subscribe button and then wait for more. Goodbye.